Hello, I'd like to show you how to use the AGGIOS EnergyLab tool to estimate and measure power for an Avnet UltraZed board. I will then also show you how we optimize power consumption using the AGGIOS Seed firmware. The UltraZed-EG system-on-module features the Xilinx UltraScale Plus ZU3-EG MP SoC and Infineon IRPS 5401 PMIC. If we take a look at the monitor, we can see the EnergyLab tool in action. EnergyLab is an integrated development environment for creating and managing the power model of your system and for configuring and generating the seed firmware for your target. On the left, we see a choice of different views of the model. By default, it's a view of the system hierarchy. I have already loaded a model of the UltraZed system, so this is what we can see here in the central area. We can see the UltraZed board at the top level containing the ZU3-EG, which is a Zinc UltraScale Plus MP SoC, but also the Infineon PMIC as well as other board components such as the DDR4 chip. If we take a closer look at the Zinc SoC, we can see the different power domains as well as the complete subcomponent hierarchy. The underlying UHA model contains all the power-related details relevant from a software and system developer's point of view. For example, we can see here the quad-core Cortex-A53 component with all of its states and their power models. What makes UHA models so powerful is that they capture the dependencies between different components as well as dependencies on the clock or voltage trees. This ensures that during simulation only such states are entered that are feasible in a real system as well. This model can easily be extended to cover your particular configuration, from custom FPGA components such as this cryptographic accelerator to a complete custom board or system. But aside from modeling the hardware, EnergyLab also lets you model your software as UHA tasks in order to accurately reflect your application use cases. A task expresses the software's dependencies on the hardware as well as on other software such as operating systems or middleware. The use case we are looking at here is software-defined radio, which requires the device to be in the lowest possible power state most of the time, but then quickly wake up when a valid signal is detected. We've created tasks such as transmit and vocode here, which depends on Linux being active, but also requires, for example, the cryptographic accelerator to be on. EnergyLab lets us follow the dependencies via hyperlinks. So here we can jump to the Linux OS task where we can see that it includes a large number of hardware dependencies, which is reflecting the Linux configuration we're using. Now that we've modeled our system, including its hardware and software, we are ready to start the simulator. This brings up the EnergyLab simulation window. This window is organized like a debugger. On the left we see the scenario file, which is essentially a sequence of timestamps and events. Using the control buttons in the toolbar, I can step through it or run until the end or until I hit a breakpoint. Our plot area now shows the computed energy profile for our use case. The red dots you see, they signify events that I can get details on by hovering my mouse over it and see exact power numbers and the detailed events and state transitions that happened there. I can now zoom in or view details about specific components or view things like transition latencies, as here where Linux resumed from a sleep state. Since I'm interested in optimizing power, I will take a closer look at this particular moment in the scenario. So I will rerun until this moment, and then I can see in the component table the details about every single component. I can also show the top consumers breakdown graph, which basically tells me what my top consumers are. But one of the components that I notice here in the table when I scroll down is the PCIe component. This component consumes 60 milliwatts, even though my application doesn't require that device. When I follow this component's dependencies, I can immediately see that Linux is the one that requires it. So let's go and change that. Here I simply remove it. And then we regenerate the simulator. And then that quickly will bring up a new version of my simulator and I can compare my results to before. So running this till the end immediately shows me a comparison against the baseline which I created before, and I can see the total power savings and energy savings in my system. EnergyLab has many other features that make it easy to further optimize power for your system using UHA models. But now I'd like to show you how we can apply such optimizations to the actual target device by configuring and generating a customized Seed Power Management firmware. The Seed configuration dialog allows me to choose from various optimizations, either globally or individually, where I can enable features such as AXI frequency scaling, DDR frequency scaling, or letting devices enter optimized idle states when unused, or by scaling the voltage of the main supply rails. It essentially allows me to enable complex power optimization features from a user-friendly UI. Additionally, Seed offers helpful diagnostic features that help troubleshoot power-related problems. Finally, I will go ahead and generate the firmware. This invokes the standard Xilinx toolchain, and once it's done, we get our custom firmware ELF file, which we simply need to include in our boot.bin file for our SD card. Let's now take a look at the UltraZed board. This board allows our EnergyLab tool to query power data from the Infineon PMIX at runtime via PMBus commands. All we have to do is to connect I2C for measurements as well as our USB cable for the UART terminals. To start the application, I'll insert the SD card including the Seed software and then turn the board back on. Now we can click on EnergyLab's Test and Measure button up here and connect to the USB port of the I2C adapter. The power consumption is plotted in the main area here, and we have the terminal windows at the bottom. On the left you can see the prints from Linux, as well as prints from Seed and the real-time processor on the right. The power plot shows the power of each power domain, but we can also drill down to show individual voltage rails for a particular domain. Additionally, the power plot shows you the temperature reported by Seed, which is measured using the Sysmon device on the SoC. Once Linux completes its boot procedure, we can start the software-defined radio application. As you can see, the system immediately enters the deep sleep state. Signal activity will wake up only the real-time processor, which validates the signal. Once a valid signal is detected, the Linux subsystem is woken up. This is where the signal processing is performed. As soon as the signal transmission is completed, the system goes back into the deep sleep state. Whenever Linux wakes up, you can see the latency reported here at just over 60 milliseconds, which is about twice as fast as without Seed. Overall, the Seed Power Management firmware has reduced the power consumption of the system by nearly 700 milliwatts in the active state by employing a variety of optimizations, including, for example, dynamic AXI bus frequency scaling or DDR frequency scaling, as summarized on this chart. At the same time, the latency optimizations included in Seed allowed our application's latency requirements to be met when coming out of the deep sleep state. I hope you've enjoyed this video. If you'd like to learn more about EnergyLab or Seed, please consult our website at aggios.com. Thank you for watching.